Probably. At the end of every chapter, there's one. So we're going to call this example 4 for section 8.6. And so far, what we've done is our first couple of questions were expanding things completely. When we expanded things completely, we used Pascal's triangle to get the numbers in front, and then we noticed the first term started with an exponent and went down by 1. In the second term, you didn't start with any of those, and then you started going up by 1. Then in example 3, what we looked at was using the formula to find a specific term. So if you want to find the 8th term, then the formula was tk plus 1, and choose k, a to the n minus k, b to the k. And that formula is on your formula sheet. What we're going to look at today are probably the hardest of all the binomial questions, and they're questions that look like this. Find the term, we'll do 2 of them, so I'll call this A. Find the term containing x to the 9 in the expansion of 3x squared minus 2 over x to the 9. So first of all, a little bit of review of what we already know about the expansion of this. How many terms are there going to be when we expand them all? 10. So worst case scenario, you could find all 10 of them. Simplify all 10 of them. Look through all 10 of them and find which one has x to the 9 and circle it, and you would be fine. Now that's worst case scenario, because that could take some time, because 10 terms going to Pascal's triangle to the row with 10 terms, and then writing them all out and simplifying all of them could take some time. But the problem right here is we don't know which term it is. We don't know if it's term 1, term 2, term 3, term 4, term 5. So when we go to the formula, we don't know what k is. In fact, we could plug everything in except for k. So if we go to the formula and say, okay, tk plus 1 equals, I know that n always comes from the exponent, so it would be 9 choose k. A is our first term, so that would be 3x squared. And this would be 9 minus k. And b is always from our second term. So this is what we have in our formula, but we don't know what k is. I'm going to show you 3 different ways that you could figure out what k is. The first way that I'm going to show you is algebraically, because there was one exam 3 years ago that said solve for this algebraically, and they only accepted algebraic proofs for it. So the algebraic way of solving for this is to say we know it has an x to the 9. So my term here on the right has an x to the 9. It has a number in front, but I don't know what that is. The only information I'm given is that it's going to have an x to the 9. So what we're going to do, since we don't know the number in front, is we're temporarily going to ignore everything that affects the number in front. 9 choose k. If k is some number, when you do 9 choose k in your calculator, you get a number. And that number affects the number in front, so we're going to ignore the 9 choose k right now. The 3 would go to the power of whatever 9 minus k is, and it would be a number, so we're going to ignore the 3 right now. The only thing we're going to look at are the x's and the exponents. So in this first term, how many x's are there going to be, and what's the exponent going to be? Well, we would have an x squared to the power of 9 minus k. And your exponent laws would say, what do we do when we have a power to a power? We multiply them. So it's going to be 18 minus 2k. And can you see that that will be all the x's that are on the top of your equation? can you see that you're going to multiply by a negative 2 over x, which is going to give you x's on the bottom of your equation? So I'm going to make a fraction here because I'm going to have some x's on the bottom of my equation. How many? What's that k going to do? It's going to apply to the exponent. You're going to have x to the k on the bottom. Notice I'm ignoring the 2 temporarily. I'm not worried about what that 2 is going to do because that would affect these dots in front, the green number that we don't know what it is. But we're using the hint that it has an x to the 9 to first solve for k. And so when we ignored everything but the x's, on the top I'm going to have x to the 18 minus 2k, because that's all the x's in the top of the fractions. And on the bottom I'm going to have an x to the k, because that's my only x on the bottom. Now, what do we do with our exponent laws? Well, this side is still x to the 9. What do I do when I divide with the same base? When you divide with the same base, you subtract the exponents. And so we get x to the 9 is equal to x to the 18 minus 3k. Now we're trying to solve for k. We're trying to solve for k in exponents. That should remind you of your logs unit. Now we have the same base. So when you have the same base, that means that the exponents have to be the same. So if I move the 3k to this side and subtract 9 on both sides, I get k is equal to 3, and that means it's the fourth term. So once you've found out what k is, and you know that it's the fourth term, now we can actually find the term containing x to 9. It's term 4. If it's term 4, we know that k is 3. So now we can plug in everything with that value. And now it becomes just like example 3 that we did before. Find a specific term. And finding a specific term is straightforward because you have your formula. Take your time, calculate each of these things separately. So 9 choose 3 is 84. This will be 3 to the power 6, 729. X squared to the power of 6 will be x to the 12. Negative 2 to the power of 3 will be negative 8. And x to the power of 3 will be x to the 3. So figure out each of those three things and simplify them separately. Keep them in brackets. Now it's all multiplied together. So we're going to multiply our coefficients together. 84 times 729 times negative 8. This is negative 489,888. And can you see that you have 12 x's on the top, 3 x's on the bottom, and that simplifies to x to the 9. So this is the algebraic way of figuring this question out. Now, the algebraic way is not the fastest way, and I'll show you 2 other techniques that we can use as well. But there are some times where they say, find the term containing such and such algebraically. And then this is what is being expected of you. So we're going to just add some things here. What did we do? We found k first. That's the first thing that we needed to do. And the key idea is we just looked at the x's. So we temporarily ignored the coefficients, all the numbers in front. So if we do that, we know that our term has an x to the 9. And if we just look at our x's, we said, well, in the first one you'd get an x to the 18 minus 2k. In the second one you'd have an x to the k on the bottom. Now, most often, if it doesn't say algebraically, for these ones, it does not take long to guess and check to figure out what's going to work. So if you had written this out here in the red box, if you had written that out and you'd said to yourself, I need an x to the 9. I'm going to pick a value of k. Maybe I'll pick 5. And it's really, I actually encourage you to try to pick one that doesn't work to start with. Because if you try to get the right one, it takes too long to guess. And if you guess the wrong one and check it out, you'll often find you figure out which way you need to go to get the right one a lot quicker than if you stay, I have to get the right one first. So if we pick 5, because I know that it's wrong, because we know the answer is 3. If you pick 5, the question is, how many x's would there be on the top of your fraction? Well, 5 would make this 9 minus 5, which would be 4. Can you see that you would have x to the 8 on the top of your fraction? And if you had 5 for k, can you see that you would have 5 x's on the bottom, which is x to the 3. And what do we want? We want x to the 9. So what do you need? You need more numbers on top and less on the bottom to do that. So we need k to be a smaller number. And it wouldn't take you very long before you say, okay, well maybe since I'm off by quite a bit, maybe I'll try 3. And if you try 3, 9 minus 3 is 6. That'll give me x to the 12 on top and x to the 3 on bottom. So I know k is 3. And can you see that might be a lot quicker than our algebra technique that we came with? And the numbers aren't big and they're whole numbers, so this is a good strategy to use. Another strategy that doesn't use the algebra is using a pattern. Some people look at what happens if we started with term 1. Well, if I would do term 1, that's when k is 0. So when k is 0, I'd have x to the 18 on top and no x's on the bottom. Then if I would do term 2 is when k is 1. When k is 1, I would have x to the 16 on top and x to the 1 on bottom, leaving me with x to the 15. And if I would do term 3, k would be 2, which would give me x to the 14 on top, x squared on bottom, which simplifies to x to the 12. Do you see a pattern in the exponents? And this will always happen. So we're going down by 3, so then it'll be x to the 9, then x to the 6, then x to the 3, then x to the 0, then x to the minus 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's the exponents of all 10 terms really quickly. So which one is going to have an x to the 9? The fourth one. And this could also, if there was a part B that said which one has an x to the 3, you could figure that out. Sometimes I would say the most difficult questions that come up with these ones is sometimes they'll say, can you find the constant term? So not only do you have to do all this math, but you also have to know a definition. What does it mean to be a constant term? Constant term has no x's. Which one of these would be the constant term? This one right there. Because it has no x's, it would have an x to the 0. So we can use our pattern, and we can use guess and check to find it. We can also use an algebraic way to find out what k is. Whichever way you decide to go with, once you find out that k is 3, right? And so this pattern technique tells you that it's T4, which means that because k is always 1 less than our term number, that k is equal to 3. Once you find out that k is equal to 3, no matter which technique you've used, you have to find term 4, which is its own, just plugging things into the formula, simplifying each part separately, and then multiplying your coefficients together and simplifying your variables to get your final answer. So I'm going to give you one to try. We'll do one of those constant term ones so we have it in our notes. Find the constant term. Call this b in the expansion of 5x cubed minus 2 over x to the 12. So how many terms are there going to be in the complete expansion? 13. So using the different techniques, no matter which technique you decide to use, we always start off with sort of putting what do we know into our formula. Well, we know n is 12. We don't know what k is. We know a is 5x cubed to the 12 minus k, and b is negative 2 over x to the k. So using all three techniques, starting with the shortest one. If you were guessing and checking and just thinking about your x's, we have what? We have x to the 3 minus 12 minus k. That's on the top of your fraction, and you have an x to the k on the bottom of your fraction. If you pick a number, we'll pick 5 again to start with. If I pick 5, 12 minus 5 is 7. That will give me x to the 21 on top. So I'll just write here, if k equals 5, I get x to the 21 on top, and I'll get x to the 5 on the bottom, leaving me with x to the 16. What am I looking for with a constant term? I'm looking for an x to the 0. So obviously, I need a lot more numbers on the bottom in order for it to cancel out. So k equals 5 didn't work, so I guess a bigger number on the bottom. I know the answer, but I'll purposely choose ones that get closer. So bigger number on the bottom would be like k is equal to 8. So we try that one. If k is 8, 12 minus 8 is 4. That would give me x to the 12 on top and x to the 8 on the bottom, which leaves me with x to the 4. I still need a bigger number on the bottom. So we try k equals 9. K equals 9 gives me an x to the 9 on top and an x to the 9 on the bottom. Those would cancel out, leaving me with no x's or the constant term. So that's finding k with the guess and check method. If you like the pattern method, the pattern method said start with term 1. Term 1 is when k is 0. That would give me 12 minus 0 is 12, 3 to the 12 is 36, and there'd be no x's in the second one. Term 2 would be when when k is 1. This would give me x to the 33 on the top and x to the 1 on the bottom, giving me x to the 32. I like to do 3 of them, even though if you do 2 and you don't make a mistake, the pattern is right. You go down by 4. If you do 2 and one of them's wrong, your pattern is definitely wrong. So if you do 3 and the same pattern doesn't happen, then you know you've made a little mistake. So for term 3, when k is 2, you're going to get an x to the 30 on top and an x to the 2 on the bottom, which leaves you with an x to the 28. And sure enough, it looks like you're going down by 4. So if you keep going down by 4, x to the 24, x to the 20, x to the 16, x to the 12, x to the 8, x to the 4, x to the 0. There's the 1, count them, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is term 10. And if it's term 10, then k is equal to 9. And finally, algebraically, if you were solving this algebraically, you temporarily ignore all the coefficients and just look at your x's. How many x's would I have on top? 36 minus 3k. How many x's do I have on the bottom? X to the k. Solving this, exponent laws say that we would subtract the exponents, and so we get 0 is equal to 36 minus 4k. 4k is equal to 36, divide by 4, and you get k is equal to 9. So whichever technique you like or you use, you should get k is equal to 9. Once you've got k is equal to 9, now find term 10. Term 10 would be n, choose k. And if we simplify this, again, do each one separately. 12 choose 9 is 220. 5 to the power of 3 is 125. X to the, this was a 3, right? 9. Negative 2 to the power of 12 is negative 512. X to the 9. Multiply all those numbers together. Just check and make sure I didn't forget a 0. No, we're good. And that would be the constant term. Sometimes in binomial expansions, you get very large numbers. They might start to make you feel like, did I do something wrong? Because I can't remember the last time that I got 14,080,000 as an answer for a math question. It's probably never happened before. Or is it like happen all the time? Question number 9 from the homework are ones like this, although they're not as complicated as this one. You'll find more good questions on your pretest like this. And again, we're going to use the rest of class to work on our pretests.